All right, so we got a couple more review problems here. It was a shorter week. This one is a problem that's actually pretty straightforward once you kind of get through their weird, um, the way they ask the question. So in the problem, you have this rod attached to a pivot, and you have a disc that slides atop. So we're looking at it from the top. It slides and hits the rod and makes it start rotating. It hits a distance x away. The rod itself is a length d. The center of it's at point C. So if we just look at what's actually happening, there's a collision that happens between the disc and the rod. Because there's a distance from the pivot point, I immediately look at torque, force times distance, remember, from that pivot point. And then the result of that is rotation. So we have to kind of look at how the rotation equations come in. So we have to go, so we have, instead of distance, we have angle. Instead of speed, we have angular speed. Instead of acceleration, angular acceleration. Instead of force, torque. Instead of momentum, angular momentum. All those types of things that are included. So we have to make sure we put those together. So the physics we have involved, as I just said, instead of having it with this screen up. So if we want to cause it to rotate, so it's asking where should it hit to get that biggest amount of rotation. So where along here should x be? It gives you three options. Should it be to the left of C, at C, or to the right of C? And to cause rotation, it's just kind of, imagine like you're opening a door. You don't push close to the hinges, you push close to the edge. So our answer there is going to be to the right of C. It gives you the maximum torque, which gives you the maximum rotation. And then in part B, they give you an equation, and we want to see if it matches with what we expect. Now, if you answered part A wrong, you could still get part B correct if you just kind of analyze it the same way. But the equation, we're looking at where it's supposed to hit, so we look what happens to x. So the more we increase x, the more it's going to increase that speed. So that was part B. Part C is basically what we need to do. So they give you a new equation, and it asks you to see what happens if it's not plausible. So for it to be not plausible, we want to see, we want to imagine what happens to the angular speed when you change these different variables. So in that equation, if x increases, the speed increases, which that matches what we expect. As you increase the speed of the disk, the speed of the rod's going to increase, which makes sense. You throw something faster, you're going to cause more rotation. But then, if you get a heavier disk, if you swing in that heavier disk, because it's in the denominator, so the heavier that disk, the slower it's going to go, which doesn't make any sense at that case when it's really light compared to that thing. So if it's a tiny speck of dust and you hit the rod with it, you get, as the denominator goes to zero, you can't that you get kind of an infinite rotational speed, which makes no sense. And then if you look at it, the more moment of inertia of the rod, the I of the rod, the higher that is, it makes it go faster, which makes less sense. The heavier the rod is, it should slow things down. But in this case, it speeds it up, which doesn't make sense. So if you look at it, there are two of the variables that work and two of the variables that don't work. So that equation is not plausible. So you could kind of look at any of the arguments in the last two and be able to get full points there. All right, so for part D, now we need to find an equation for omega. And they give you the idea of angular momentum. So generally, angular momentum, L, which I still don't understand why it's L. I think at some point I had an explanation, but I don't remember it. But the angular momentum, just like linear momentum, is mass times velocity, but because we're looking at angular, instead of mass, we look at moment of inertia and angular speed. So that angular momentum for the disk transfers to the rod. So it sticks, and so all that momentum transfers. So they give you that angular momentum is also equal to the mass of the disk times the speed times the distance. So momentum times distance is angular momentum as well. But we're looking for omega, so we need the moment of inertia. And this is the one thing that I don't like about their notation. They just use the generic I for the rod. It should be like I sub rod or something like that. But the way I'm going to write it is that the total moment of inertia, so when the disk hits the rod and sticks to it, you have to add that mass. And because it's rotation, it's not just mass, it's moment of inertia. So you have to add those two things together. So the total moment of inertia is the moment of inertia of the rod plus the moment of inertia of the disk. It's like if we were doing a collision problem and the thing stuck into the bullet stuck into the block of wood, we have to add those two masses together. So plugging in those results, you get that angular momentum, which we saw was m disk v0x, equals moment of inertia times omega. So then we can solve for the moment of inertia, and you get this kind of ugly equation. Now, I think this is a bad question, and I wouldn't have asked a question like this were I in charge, but I found it, and every once in a while you get weird things on AP tests and finals. This one was more to just kind of talk a little bit about angular momentum and moment of inertia, but as it's going through there. So that's what the equation looks like. All right, and then the last part, if it bounces off, hopefully you remember we've been doing this a little bit, is when you have it bouncing off, not only do you get the transfer of the moment of inertia to stop it, you get an additional transfer of momentum when it bounces back, so it's going to make it go faster at that point.